Welcome, everyone. My name's Adrienne Brown. I'm the LACCD District Academic Senate Professional Development College Coordinator, and I'm very happy to see all of you, see or hear all of you, since some folks are going to keep their videos off, here to learn. I wanted to say that this event is sponsored by the West LA California Center for Climate Change, and it's a state center that's housed at West LA, but there's two different groups within LACCD that are working on climate. West LA, they're working on climate solutions and job creation to meet the demands of the future workforce and climate change. But the hosts of this event is the Sustainable Environment Institute, and let me tell you about them. So their job is to get concerned faculty of LACCD to promote environmental awareness through curriculum, job training programs, and in our daily practices within our district. And so it's really wonderful to have you all here. As you know, we've only got one habitable planet that we live on, and this is crucial information. It affects and impacts all human beings and all living beings on the planet. But it also applies to every single discipline. And I've attended other professional learnings put on by the SEI in the past, and so you are in for a treat. I would like to introduce George Leddy, Beth Abels, and Chow Behlendorf, who are all three here to introduce the speaker for today. You will see that they have got an amazing website set up. Definitely check it out. They've got a newsletter that comes out regularly. Read that and keep coming to the workshop series, which is one that you're going to get to experience today. Welcome, everyone.
Thank you, Adrienne. Well, we'll get started. I want to welcome everybody to this our series of seminars from the Sustainable Environment Institute, where this fall our topic area has been urban heat and the heat island effect. So this is actually our third seminar on this broad topic, but with a very unique contribution made by Dr. Yi Yin, who is now faculty at NYU in environmental studies. And you will see that her work is actually very scientific. She is a graduate, twice graduate. Her doctoral degree is from University in China, and she has great preparation in quantitative analysis, and also in something we welcome very much in my environmental science class, the visual representation of quantitative data. That's a mouthful, but what it means is that sometimes we can see numbers better than we can see tables, columns and rows. So without delaying any more, let me immediately move into what is the introductory section, which we have as a tradition to introduce the topic and some of the terms that might be used as we move forward. So Dr. Yi Yin is a research scientist. She continues to be affiliated with the research faculty at Caltech and now on the faculty at NYU. And what we're always examining is, of course, the major problem of the increased temperatures on planet Earth and how dramatic that has been since the 1980s. So this chart is just to remind us that, you know, if there were any trends before World War II, it was actually towards some cooling effect. So this is what we call anthropogenic climate change. This is a climate change that has been produced by human activity and not by longer-term natural cycles. This is our fair city on a bad day. Maybe we've made some improvement in air quality in Los Angeles thanks to air pollution standards and changes in vehicle emissions and so on, but we still are the most air polluted city in the United States for a large metropolitan area. This Washington Post article actually looks at the case of Kolkata in India. I recommend it because it also has very useful visual representation of concepts that people dealing with urban development and the science of urban planning take into account when it comes to very high temperatures experienced by, in this case, the poorest people in the city of Kolkata. This article is one that deals with the urban heat island effect in a completely different context, but I thought I would mention that Dr. Yin is actually part of a global effort by environmental scientists to get more, what is the term that's used? Granular in terms of the data and in terms of what can be done when it comes to public policy outcomes. So the heat island effect, what you're seeing here is essentially what we all experience when we drive downtown. It's often hotter. There are dark surfaces, there's asphalt, there is rooftops that are tarred, so that the heat absorption by automobiles and buildings makes the urban core considerably warmer than the more forested, if you want to use that term, suburban areas, and of course the more the wilderness areas or undeveloped areas outside the city.
The majority of Americans live on islands. They're just not the usual kind of islands that you're thinking of. They're urban heat islands.
What's happening is heat is literally getting trapped in this urban center. So if you can think of a dome overarching the city, all the carbon emissions, whether from the buildings, from all the people within it, or just traffic, that plus air getting trapped within the tall buildings and the narrowly placed buildings, all of that is building and building, and it has nowhere to escape. A New York-based study that measured temperatures between the South Bronx and Central Park, and there was a 20-degree difference during the daytime. The difference can be as far as 22 degrees Fahrenheit, even at nighttime.
So the big question will be adaptation. Do city planners really start thinking about what they need to do to make cities more livable as temperatures are rising?
There's really almost three ways of doing it. One is literally planting more trees, creating more urban gardens, creating green spaces. And the other then is to look at how do we either retrofit buildings, create living rooftops, paint the colors of the rooftops white. And then the third is really helping communities when there's a heat wave coming, to alert those communities, but also to be able to respond, whether it's providing water, whether it's checking in on people, and just taking care of people.
It's a huge menu, and too many places are looking for the one thing they want to order, when it's really like, let's get one of everything and try it out.
So what we're looking at is this bridge between science-based public policy, or this bridge between the scientific community and scientific research and the outcomes, which would be solutions to environmental problems that happen, of course, across the board in society. But in this case, we're very interested in what local, county, and state of California can do to address the particular heat island problems of the city of Los Angeles. Dr. Yin is, as I mentioned, now very fortunately at New York University, and her focus is on the complex interplay of carbon, water, and energy between Earth's surfaces and the atmosphere. So this combines atmospheric sciences with chemistry. As most things in environmental studies and environmental science, it's multidisciplinary. That is, you gather data using different methods and optics and put them together in a cogent observation, statement, conclusions that bring in all those different sources of data. So the paper that was published by Caltech is called Low Income Areas Experience Hotter Temperatures in LA County. This paper we've posted on our website, and I hope that people will visit that. You can see the address of our website right behind Beth Abels and myself. And you'll also notice that it encourages you faculty to fill out a survey that we've been undertaking now for 2 months on your experiences with the SEI and what you would like to see us doing moving forward. So it came out April 28th. It's a recent article, and it has really, well, I hate to say caused a big splash, but it has. And there are, as you can see, quite a few researchers that took part in this research article. I recommend to my students in environmental science to not be intimidated by scientific papers. We actually spend one semester in my lab class adopting one science paper per student, and students learn to get over their fear of science papers, learning that they are actually very well structured. They have a certain method to them that makes taking them apart easier than anything we do in social sciences and humanities. So I do encourage people to have a look at this paper and maybe even include it in your course materials as you discuss Los Angeles. So this is the most compelling of all of the images that are in that paper, and you can see that, as usual, a picture speaks 1,000 words. So at the very top, you see this correlation with income, the median household income. And then on the bottom, you can see what are the spatial patterns and correlations. And this has to do with land surface temperatures, with income, and with vegetation. So that is why these three maps are quite distinct. And then you can see the use of color to highlight those contrasts between the urban core and, of course, the very hot areas up in Lancaster and Palmdale. You have the very hot land surface temperatures. But it is something that, because it's visually represented, is useful even to those of us who are lay people and do not have doctoral degrees in environmental science. So land surface temperature is something that Dr. Yin will talk about. And NDVI is the normalized difference vegetation index. It's a mouthful, but think plants and the role that vegetation plays in cooling areas off. We've had in previous seminars tree people discuss with us the need to plant trees in those neighborhoods that have no trees at all and what difference that makes to the quality of life. The albedo is what is reflected by the Earth as a whole. You could call it the shininess of the Earth if you're taking physical geography. More locally, you're talking about the reflectivity of local surfaces of a body or a surface. So that is something that Dr. Yin will actually refer to. And then you can see these are once again, looks overwhelming, but it's not. It's actually quite simple. Day and night differences in the seasonal distribution. And then it goes on to discuss household income. So this is the correlating and very compelling correlation of income and what people experience in terms of their quality of life. So this is the hottest year of the hottest year of the hottest year. We seem to break every record every month. And there I will let Yin speak to us all about her work and why we need to use this kind of work when we devise new public policies. So there we go.
Thank you so much, Professor Landy. This is a fantastic introduction, and I think there are so much train of thoughts that also I strongly echo with. And thanks a lot for giving the background. And I think I will reiterate a lot of what you have just said, just from slightly different angles, maybe. And also, I think one important thing that we wanted to do is that by share the make of the science to demystify some of these sort of like George just mentioned that scientific papers are not that scary. And so I want to highlight here the contribution from my co-authors, and in particular, our former graduate student, Li Yinghe. She's also here. So at the end, she will share using this QGIS, which is an open source GIS software, how we can look into the data per different area, and again, like just share the make of the science so that we can democratize data and with more people looking into it, and then trying to find solutions for the adaptation, and then having more mitigation efforts towards climate warming. Now, George has just mentioned the background of our age, climate change, and the temperature has increased. Now, I wanted to show this change in a different way. This animation will show global monthly mean air temperature since 1988. And you probably have seen this before, but I really wanted to show this here so that we are all reminded about how much the global has warmed over this 120-year period. And so the circle is for a full year, and then the distance towards the zero is how much it has deviated from this mean across these 120 years. And as you can see, in recent years, it has become a lot more warm. And I personally find this as a very unraveling way of showing how much we have really, the global average temperature has increased. And in some of the years, the average has been higher than 2 Fahrenheit degrees than the average, which is a lot. And so same thing, but showing it from different perspective. On the left-hand side, it shows the surface air temperature, global average, over June, July, and August. And 2023 is the highest on record, and it's like as George just mentioned, that it's the hottest year of the hottest year, and we kept breaking the record. But this year, I wanted to say that it is also not a little bit higher than the past. And as you can see, and I'm not sure if you can see my mouse cursor, but then 2023 is really an outlier in terms of global mean air temperature. Now, on the right-hand side, it shows the daily sea surface temperature, which also warmed up quite a lot during the past decade. And then again, 2023 stands out. It's not a little bit warmer than the previous years. And it really, I think the climate research community are still scratching our heads of what this really means in terms of extreme climate. And so I mentioned all these, and yet it's still an average. But I think all of us know that no one really experienced the global average temperatures, right? We experience the temperature in a particular space and particular time. So it is really important to look beyond the mean and at the distributions. And this is a very informative plot that shows when we talk about global warming or the increase in the global mean average temperature, we have first a shift in the mean as shown on the left, that the average is higher. But also we have an increase in the variability, that we have more extreme events on both ends. And as you probably have directly experienced or read from news, that we have increasingly more intense, more frequent, and with longer duration of extreme, in terms of both extreme hot, extreme precipitation, and also extreme cold events. And it is really all the climate extremes that is almost like the most profound ways that climate change impacts ecosystems and human societies. And so it's a very critical area of research. And I think it's also very critical in terms of how it shapes public opinions about the risks of climate change, and hence the commitment in the mitigation and adaptation efforts, which is why my research focuses on extreme climate events. And I want to say that even though I put US as an example here, it is not a US problem, but a global phenomenon. And arguably, if we look across the world, the tropics and subtropics are those that suffer most. And this map here shows the global heat wave exposure, and each of the dots represents the population size, and the temperature shows the air temperature, and that is a very deadly air temperature. I will compare this difference between air and land surface temperature in a bit. But that said, I think there is not much disagreement, I think, in terms of we have observed all these changes in terms of air temperature. And another factor, however, is the urban. And George already introduced this concept, and I like that video, kind of highlighted how urban, because of this reduced vegetation, high population density and construction, and also a lot of waste heat from that's directly generated by human activities, that city centers often experience much higher temperature than the suburban. And that said, also an island is not really a circle, and there is a spatial variations, so that different communities will experience different temperatures. That is one of the things that our study particularly looked into, is that within the city, and also Los Angeles is kind of special in the sense that it's not a super compact, but have different subcenters. And we will go into that a little bit later. And also heat is not a single isolated fact, right? Because often when the temperature is very high, we also tend to have bad air qualities, because the higher temperature is favor some of the NOx and the ozone production, and that is another health effect. And also because of the we have so much impervious surfaces, that if we have a strong precipitation, then they accumulate into flood risk very fast. And in addition, that with this heat, super high heat, and then we have increased wildfire risks, that we have also witnessed during the past years. So it's a lot of things hit, and in terms of a health impact, in addition to that, the health illness that we hear most, like dehydration, heat stroke, or the attack on people who has already some chronic diseases, it also has been more and more evidence has shown it has, for instance, negative impact on mental health, and also it reduces physical work capacity, which when it happens often enough at the large scale, that is a strong hit on the economy and the development of city. And yeah, and in general, it's more like the well-being of the citizens living in the urban environment. So all this said, it gives us strong, I hope you are convinced now that heat waves and is a really serious threat to public health, and we should treat it very seriously. And however, the city are not made all equal, right? There has been studies that documented that within city, there are different populations for different racial or economic status experience different temperature. And this is repeatedly found across a lot of US cities. However, the past studies mostly looked at a relatively like a categorical differences. But what we wanted to do really is to room into Los Angeles and ask this question and to go to the bottom of it. Do we observe consistent disparities in the heat exposure across the Los Angeles area? And what are the dominant factors in the urban setting that lead to such a disparity pattern? And what are the potential pathways for equitable adaptation efforts? And before I dive into these questions, I want to show this animation that shows the staggering speed that urban area has expanded since 1977. Yeah, it is a very rapid and marvelous development that I have to say. And actually across a history, the point where there is the highest population density was actually the very beginning. So with the development, even though we have increasing population size, the city area has always been expanding so that the population density is actually going down instead of going up. But behind that, it's the fossil fuel, right? That has been powered all the automobile, the spread of the city, and the massive construction of the highway, which shaped our high carbon footprint today. And that also comes with a cost, which is the warming that we have to deal with now. And again, also this process, it favors some of the communities more than the others. So I think it's very important to look into regional disparities across those communities. And I want to, before I go into the technical details, I want to start a little bit about the basics of surface energy budget. So it's really quite simple if we think about simple math in what the changes in the energy of a system equals what energy comes in and what energy comes out. And the most important energy coming in is the energy we received from the solar radiation, right? This, as shown in this yellow arrow, which is the shortwave radiation. And in the sky, some of them, top of the atmosphere or through the clouds, are reflected back already. And when they reach the surface, a fraction of that is also reflected, as shown by the orange arrow, so that the reflectance, which is albedo, the buzzword, which is the percentage of energy that is being reflected back, which is this alpha S, the short wave, that will go back to the atmosphere. So what really reach or being absorbed by the surface is this short wave radiation and minus the part that reflect back, right? That's the energy in. And in terms of energy out, going out, then it's mostly the non-wave radiation, and then also some turbulent fluxes of the sensible and the latent heat. And the non-wave radiation shown on the right hand by this curved arrow, it is a function of the temperature. And so that the air surface, when it heats up, it actually being able to radiate out more of the non-wave radiation. That's kind of the temporal equilibrium where it would be. And however, a very important aspect is this latent heat, which is shown in the blue arrow. And I think we all probably have this experience that if when you go out and get out of the swimming pool, when you sweat, it can take away some of the excess heat. So it's the same for human being, and it's the same for the surface. And that is one of the most important ways for the surface to dissipate heat. And then this G term, which is the ground, take up some of the energy, and that results in changes in temperature of soil, plants, water, and air. So that is generally this case. And for a city like Los Angeles, in general, everywhere receives pretty similar shortwave radiations. And if an area has more clouds than the other, yeah, of course, there is some reduced amount. But in general, that term wouldn't vary that much across area. So what makes the difference is really which ways the surface could get rid of those excess energy. And I will dive into that in a bit. And so for our research, we use a lot of satellite remote sensing data. And what is shown here is land surface temperature retrieved from a satellite called EcoStress. It is a NASA instrument on board of the International Space Station. And the color shows the temperature, the land surface temperature, which is the skin temperature at the surface. It's like the temperature when you touch it at the surface, but not the air temperature. And so you can see through this area, as I mentioned already, that there probably isn't that large a gradient in terms of shortwave radiation, but we can see that the gradient in the surface temperature is very large. And if I zoom in into our beloved Caltech campus with this red heart denote, and we have Teuton on the right, if I overlay the surface temperature on top of that, we can already see a very significant gradient. And on the lower part, it's more bluish, that's cooler, corresponds to areas that has more vegetation. And also we have slightly lower temperature around 210, and that mostly is because they have a higher albedo compared to this observation angle, because they are more like cement surface that has higher albedo. So it's slightly cooler compared to those very dense buildings. And then the circles, I wanted to see the circles refer to those artificial turfs, because they have a relatively low surface albedo and also relatively low heat capacity, so that they really heats up, and as opposed to real vegetation. And a little more on the vegetation. So in general, we see this gradient that vegetated area are cooler. And we know that the temperature of objects, including us, reduce temperature by evapotranspiration. And evapotranspiration by plants, they can cool the leaves, which is why sitting under a tree is cool. And this is both because of the shading effect, and also the leaves are cooler than the surrounding objects. And then the turf, the universal turf are very hot because they don't have any ET to dissipate the heat. With this in mind, we also look other satellite remote sensing data from Landsat 8, which gives you the surface reflectances in different wavelengths. So with that, we can calculate the effective albedo. So how much of the shortwave radiation would be reflected back, and also the greenness index and NDVI, normalized difference vegetation index. Yeah, it's a very convolved term, but we could simply put it as a way of how green the land looks, which represents roughly the percentages of vegetation cover or how healthy they are. And another element that I wanted to mention is this redlining historical housing policy. And on the left-hand side, it shows over from 1939 to 1928, over these decades, and there has been this housing policy so that different districts had different gradings, and based on that, the investors likely or less likely to issue home mortgage, and that has become a factor disadvantaged a lot of neighborhoods that do not have this effective financial resources of maintaining and building better. And on the right-hand side, it shows for the different categories, with red being the historically disadvantaged and blue being the historically favored, that the differences in the land surface temperature really are very, very different. And this is, to me, still very astonishing. If you think it is a policy that is over 60 years ago, and it still has such a systematic impact on the current landscape, I think that is something we as a community should be very aware of, and how to compensate and to mitigate for such kind of inequalities. And then moving beyond, I think George has already showed this 3 map, which shows the land surface temperature on the left and the median household income on the center, and then the NDVI, which is a greenness index on the right-hand side. Each of these polygons shows a zip code area here. And as you can see from the next slides, each of the dots represent one of the polygons. And here on the x-axis, it shows median household income. And then on the y-axis, it is the land surface temperature. And this is one image that overpasses this area around the noon. And then we use a very simple method called linear regression, and that calculates the slope of the differences in the land surface temperature against the differences in the median household income in the x-axis. And this slope could then be used as a metric to measure the inequality. So how different in the land surface temperature would result from a certain differences in the median household income. And then on the right-hand side, it shows the median household income as the x-axis, and the evapotranspiration on the y-axis. And as I mentioned earlier, evapotranspiration is the term to measure how much of the heat could be dissipated through by changing water from the liquid state to the gas state. And that's basically come from vegetation. So ultimately, I think it is the differences in vegetation distribution that shaped the differences in the land surface temperature. And if there is a burning question, I can take something now. And if not, I will continue. Are we all good?
We're all good.
Sounds great.
Thank you very much for checking in.
Of course. Okay, so here, it's basically the same thing. And I wanted to first just to focus on the upper left. It said on the y-axis, slope land surface temperature against income. So which is the slope we derive from those regression. And then the x-axis is different local hours. So when it becomes more negative, it means at these local times, say around noon, we find a larger slope, that is a larger difference in the land surface temperature due to across neighborhoods with different income. And then on the lower side, the plot on the center shows R, which is a correlation. How strong are these two variables correlated? And on the bottom, it is the count. So how many images do we have at that local time to measure the different surface temperature across Los Angeles? Oh, and something I forgot mentioning, and that's actually quite important, is that EcoStress measures land surface temperature at a very high resolution, and the composited data is around 60 to 70 meters. So we know the temperature, we can measure it at a 70 by 70 meters, which is really very good resolution if you think that about the scale that we are analyzing. And it's cool. And EcoStress is also the first satellite mission that can measure the surface temperature at different times of the day. So it gives us the opportunity to look at the diurnal variations of those disparity patterns across an area. Because previously, more polar orbit has revisited around the same local time, and it may not necessarily catch the peak disparity. And here we even get data over the night so that we can have more full picture about this disparity pattern. And then, so upon now, what I showed is the aggregated analysis per zip code. And one may ask, well, within one zip code, there are still diversity and there might be gradient within the zip code, right? And is that robust if we do it at even finer scale? So we did the test at a block group from the census. So it's even higher resolution. And as you can see on the left-hand side, now it is also this median household income distribution per block group. And then we have that surface temperature in the middle and NDVI on the right. And then we filtered out some of the forest area and that. And then we did this analysis yet again. And on the left-hand side, it's median household income against land surface temperature. On the right-hand side, I think it's for a different time of the day. And to illustrate how they look across, so on the left-hand side, I have some neighborhoods, and you can see through visual inspection that there aren't that much vegetation, and on the right-hand side, there are. And then we will also want to account for other geographic factors, right? For instance, the distance to the ocean. Like we all know that when you are closer to the ocean front, the temperature tends to be cooler. And is that a strong factor explaining the disparity pattern we see? And one can see that, yeah, there are some of the correlations. And however, it's not explaining the majority of the variations that we see across neighborhoods. And also, how about elevations? And when you go up and like different elevations or a different slope aspect, if the slope is facing south or slope is facing north. So in general, we analyze quite a few geographic factors. They do not seem to explain all the patterns that we see. So to the bottom of it, I think vegetation cover really is one of the dominating factors that shape this disparity pattern. And then how about the surface albedo for areas that do not have vegetation? So we removed all surface areas that has tree with a few metrics, and then we focus on areas that is pure built surface, which would be rooftop or highway, and then we look whether there is a correlation between the land surface temperature and shortwave albedo. And the plot on the right-hand side shows this quantile regression, where with the x-axis is albedo and the y-axis is the land surface temperature. And statistically speaking, when the surface albedo is higher, which is more of the solar radiation gets reflected back, it tends to be cooler. And that has been proposed as one of important ways for the mitigation. Now, taken together, we're adding all the 200 images over the 4 years that we connected the data, and we put it against the mean regional temperature. You can see that the magnitude, as shown on the right-hand side, the magnitude of the disparity really increases when the temperature is high. So the takeaway is that when it is hotter, we see a larger difference. And then the correlation kind of saturates when the regional average temperature is around 20, but the slopes just kept increasing, which has a very strong implication, saying that going into the future, and when we have more heat waves, higher temperatures, if everything stays the same without effective, equitable adaptation efforts, we are going to see an increase in this kind of disparity. And I think that is a very important message to come across. And last, I also want to talk a little bit about the limitations of the land surface temperature. And the land surface temperature is the surface skin temperature, which is very different from the ambient temperature that we directly experience. However, they are very much correlated. But due to limitations of a lot of things, we do not have a very high resolution to really resolve intra-city variations of the air temperature. And I think that is really an opportunity for citizen science and how to connect more valid, reliable air temperature and humidity data from different mobile platforms so that we can make more well-informed decisions regarding future mitigation. And another aspect regarding the the direct observable impact on human health, is that the map shows the excess ER rate during heat waves. It's like if these days are heat and the 3 days across that, we calculate the ER terawatt rate, and which kind of is a metric of how much excess ER visit we have. And that correlates very strongly with median household income, and it happens way often than in hot days hot areas than the relatively cooler areas. So I think this also it's a very preliminary analysis on this. We're doing more work regarding those to connect the heat exposure to medical data. But I think as a first preliminary, it shows that they do face different risks. Now, as we want to spend some of the time to talk about adaptation pathways, and I think this nice summary that George put in the beginning already allude to this. So plants are good. They can do a lot of things for the ecosystems, and they provide shades, they reduce energy consumption, they improve air quality, with the caveat that sometimes some of the trees emit VOC that may impact the air quality, so that we need to be very mindful about what kind of species we choose for certain cities, so that they are both water use efficient and do not impair air quality. And also, I find this plot online, it's really interesting that it also says that it increases your house market value. Very Los Angeles. And that said, there are a lot of physical limitations to this, like a geomorphic, I think, more detailed understanding and study, and which for the currently disadvantaged neighborhoods, are there physical spaces, and could we support those? Because planting tree is one thing, and maintaining it often requires even more resources. And also we are in a semi-arid area. Where can we provide sustainable irrigation to support all these trees? And maybe there is a certain sort of species complementation with some vines. So it's a lot of some built structures. And also cool roof, which has been mandatory in Los Angeles County since 2015. So this is very encouraging. And then you probably have heard about projects such as cool pavement to add a coat on the road so that more heat is reflected back. I think there are still a lot of debate regarding whether it really increase the human benefits, because if you think about the energy budget, when you reflect it, and for roof is fine, right? Because it's higher, and if the heat is reflected back, it is easier to dissipate into the free troposphere. However, at the surface, if pedestrians are just walking by and more heat is just reflected back to you, it may not necessarily be that beneficial. I think there are still a lot of experiments, but I think those are necessary steps to figure out what works. And it may not be one single thing, but a combination and different conditions with use different strategies. And then also, I think, adding to that, the limited water availability. And I think a lot of recycling and how we effectively retain rainwater, and which has the benefit of both reducing flash flood and also make use of this water through natural rain gardens, wells, underground filtration trenches, to really increase the residence time of water in the ecosystem, and also as a side effect would help with flood risk and also some of the pollution. So with that, I will end here. I think I have the summary here, and then there is my email. Please feel free to reach out. And as I said at the very beginning, I think some of the motivations for us is really to demystify how we get the data and discover those patterns, and how we could contribute to the community to really make meaningful changes. And so with that, I will end here. Maybe Lynn can take over and show a little bit of the data.
Okay, yeah, good. Yeah, I will share my screen now. So before showing the geographic information system, I have a couple of slides. So hello everyone, thanks for the invitation. So my name is Li Ying, and I was in the same group as Yi Ying. So I'm very honored to be involved in this project and contributed to the data analysis part. So today I will share you some experiences in dealing with different data sources in this project. So as ecologists, every day we work with geospatial data. So geographic information system, also called GIS, is a computer system developed to manage, display, and analyze all types of geographic and spatial data. So using GIS, we can easily see, analyze, and understand the spatial patterns and the relationships between different variables. For example, we collect data from different sources, including street, buildings, and vegetation, and we put them together into the computer system as different layers, and then integrate them together. So the computation of the geospatial data in GIS is all based on the geometry analysis. So the data used in this project mainly from two sources. One is satellite image, and the other is socioeconomic data. So for satellite images, we use land surface temperature and the vegetation greenness. So the vegetation greenness is what we use here is NDVI. It's a widely used metric for quantifying the health and the density of vegetation on a given area of land. And also we use demographic data from US census with a spatial focus on the median household income. So then I will open the GIS software to give you a taste of how we process these data sets in the computer system. Okay. So here we show, we analyze the data in the system called QGIS. So first we open this background map. So it shows the geographic features of Los Angeles County. And then we overlay this land surface temperature map from EcoStress satellite. So this image was taken from 2021, June 4th, and around 1 p.m. So it is in the afternoon. So you can see the color bar here. So the blue means the surface temperature is lower, and the red means higher surface temperature. And then we close this layer and open another layer. This is the NDVI map. So it's the surface greenness map from Landsat satellite. So it is was taken in the same period, 2021, and in the month of June. So you can see, so it describes the density of vegetation, and green means more plants. And for example, these mountain areas, it's more vegetation here, seems more green. And also for here in downtown Los Angeles, so you see it is more like yellow, so it means less vegetation here. And then we close this layer and open another layer called, so this is another layer describing the median household income. So it is at the level of zip code region. So for here, if you see this color bar, so the blue means the poor regions, less income, and the white means the income higher, so it's richer regions. So for example, you can see here is more blue, so it's lower income regions, and here more white is higher income regions. So what we did next step is to overlay these two satellite images with this income geographical data. So because this income data gives us the boundary of each zip code region. So we overlay these satellite images with this data so that we can extract the greenness and then surface temperature in each zip code region. So for the purpose of time, I will skip the processing here and just show the results. So after doing some data analysis, we get this result. So this is the zip code level and surface temperature. So you can see the blue means lower temperature, and red means high temperature, and also zip code level vegetation index. So green means more vegetation here. Yeah, and I think I can stop here. So hope it is useful. And if you have any questions, please feel free to reach out to us.
Thank you, Dr. Hay. This has been incredibly informative, and I know that we have quite a large turnout today, including our faculty member that teaches GIS, but I'm sure that in terms of the disciplines covered for this presentation, it's been amazing. There's geography, there's chemistry, there's economics, and what we say is you can't manage what you can't measure. So here we have very careful measurement that should provoke us into a more granular management of what happens in our urban core. I know there's many questions in the chat, so I want to turn it over to Beth Abels and Xiao Bellenhorf to let you know what some of those questions are. And maybe we can get that within our time frame. Thank you.
Yeah, so there's a question here about removing lawns and its effect on the heat island. And whether replacing them with gravel or concrete was helpful or maybe not so helpful.
I think there are many aspects to it, right? The motivation of removing noise is to save water. And so first I wanted to say turf grass, it's a very wasteful way of outdoor water usage. And if we are thinking about the benefit of having vegetation, per area, it uses water, I think it's like around 3 or 5 times than an actual mature tree. So that said, I think it's not a very effective way and to conserve water. We and it doesn't really have shade. So it's not a good way. And then by moving all the way to desert landscape or gravel, then we would end up with more higher surface temperature. And I think there has been a lot of debate of how we should use water, and water is very limited in California. But however, arguably over 85% of the water goes to agriculture. And a large portion of the agricultural product is for exporting, right? So to a degree, we are exporting the very precious water. Not really, not only it's about exporting agricultural product. And I think if we think through all this, does that really make economic sense, or what is the priority? I think that opens questions for a even bigger question. Now, going back to this backyard landscape, I think the best in an ideal case is to have these more native drought resistant trees, like a lot of the oak trees in Los Angeles, that can provide shade, and they are relatively conservative in terms of water use, and they are relatively resilient to drought. And then we also have a lot of palm trees, which is very iconic for the LA city view. They are beautiful, but they don't really do that much for shading. So I think there are so many different aspects, and it's hard to have the right answer. I guess it's how we think about our thank you. I thought there are some of the oaks. Palm tree. Yes, yeah. I was advocating for oaks. Okay. Anyways, I hope that answers this question, but it's not a straight answer. And in a modeling world, when we remove all nouns and change the sorry, I shouldn't look at the chat. I get distracted. That in a modeling world, if we replace all the vegetations and have only desert landscape, we do have on average a higher air temperature as well. But I think the jury stay out of that. Yeah.
And speaking of air, there's a question here as well about the relationship between smog and heat, and how the smog might change the temperature, or the lack of smog might change the temperature.
So it's more that in a higher temperature, it tends to excite all those chemical reactions, so that we have more secondary particle forming, and that is a health hazard. And so sometimes like a personal experience may, I think statistically speaking, and in both observational and the modeling world, when it gets higher, because it excites all the chemical reactions, we tend to have worse productions. But again, when you zoom in into different regions and different scenarios, it may differ.
Sorry to interject. I'm just noticing that our colleague, Dr. Joe Tavares at the Climate Center at West LA College, has a suggestion for faculty on this call for materials. And in the time left, I would like to give Joe Tavares a moment to explain what that center is doing. They did co-sponsor today's event, and we're looking forward to Climate Palooza next week. Go ahead, Joe Tavares.
Hi, everyone. Thank you so much for having me here. Dr. Ian, thank you so much for sharing all this knowledge, and thank you for conducting this kind of integrated research, bringing science and justice issues together. So I wanna reinforce what I wrote in the chat there. I'm here with Alekas, one of our interns. By the way, here's our center. We have more students working over there. And students are really interested. They want to do more. Yes, I showed you all. They want to do more. Students come to us and they want to get involved. And so if you're faculty and you have an idea on how to get students involved in this kind of research that is applied to their lives, right? We serve students that live in those low-income neighborhoods that Dr. Ian and Dr. Him mapped. And so they come to us and they say, I want to do something for my community, for my neighborhood. And they're studying. So we could empower them in many different ways. So if you are working on anything that could be remotely connected with the heat islands, be it human health aspect or data analysis, GIS, mapping, whatever you want to do, connect with us, communication as well. Connect with us and let's discuss because we can help.
Yeah, thank you so much. Yeah, I think at both ends, it's really beneficial, and no one can solve a climate problem, and it really need to evolve. And I think local knowledge is really important, based on each local station to have a very specific mitigation and adaptation plan. I think that's very critical. And one reason we were sharing all this data is to wanted to show the infrastructure and also how we could provide the data and methodology for the community. Yeah, thank you so much.
Well, thank you both, Dr. Yin. This has been a wonderful turnout we've had today. We're delighted, really, and it shows the success of this whole series on urban heat and the interest that it's raised among our faculty and even possibly some of our students. I'm hoping mine are checked in. So we've come to the end of our presentation today, but I want to encourage people to visit our website. That's right behind me over here, where we have every time we have a seminar, we have the complete recording available as well as the introductory section and ancillary documents, and that would include Dr. Yin's biography, and Dr. Hay, if you want to contribute that as well, so that people will know the incredible quality of work that's been done and how important it is to use many optics, many disciplines and approaches to making a cogent comment about what it is to live in Los Angeles. So as an interdisciplinary professor of environmental science, I am absolutely thrilled that we've been able to host you today. I would like to, Beth, maybe, or Zhao, to say anything else that we might need to add before we close. There is a heat and equity seminar evaluation. I think I'm looking at it, it's a poll. So we're polling attendees if you want to answer any questions on the poll. And also thanks to Joe Tavares and the Climate Center at West LA College for co-sponsoring today's event. And we're looking forward to the 3 days next week that will be spent on climate at West LA College. And that's both in person and remote. You can find links to that on our website and our homepage on our website. Beth, anything to add before we sign off?
Thank you, everybody. Fill out the poll, check our website, make sure you take the survey if you've haven't had a chance to. And thank you to our speaker and to graduate students. And also thank you very much, Adrienne Brown, for being here and introducing ourselves. And we look forward to seeing you again at the Climate Palooza and also on November 12th at our next seminar.
Yeah.
Thank you.
Yeah, thank you so much. I realize I haven't addressed all the questions. So if you do have questions, please feel free to reach out.
And your email was actually in the chat, right? So that people should be able to find that.
Yeah, if you have a question, please, if you want to share it in the chat, we will make sure it gets to Dr. Yin for you. So.
Thank you.
Merci. I'm going to do my